All right, welcome. My name is Jeff Hancock. I'm a senior product manager here at Mentor Graphics. So yes, I'm going to talk a little bit about harnessing the power of multicore on an SoC out here. These talks are meant to be just kind of give you a high-level overview on some things, and if there's anything that you want to talk more about, deep dive, I can definitely stay after here. So what we've seen this over many, many years is the semiconductor guys, they're trying to be as helpful as possible, right? So they start adding a bunch of new features, functionalities into their silicon out there. And a number of years ago, they decided, you know what, one core wasn't enough. So we're going to add multiple cores out there. And then they said, you know what, there still is not enough compute power or functionality, so we're going to add specific cores out there. So maybe we have a safety island that has multiple cores, application CPUs out there. And then maybe we'll add some other capabilities out there. And so why would they want to be able to do this, right? So it helps from a hardware consolidation standpoint. I can now have systems that were spread across multiple boards and different component systems within there, now on one device out there. Why would somebody want to do that? Well, obviously from a perspective, be able to reduce bill of materials, aka cost out there. Power consumption is some other things out there from that you can leverage benefits out there. But then also be able to increase the capacity and performance of the system. But by doing all this, they made things really, really complicated out there. So how are you going to be able to develop out there, debug? If you have safety concerns out there, how are you going to be able to meet those safety demands out there? So once again, right, so I already talked about all those different cores, but oh yeah, they threw in some FPGAs in there, maybe some other soft cores, DSPs out there. So now you have like these heterogeneous environments, right? So if I throw on top of that the software, so now your software for a system starts to even become even more complicated, right? So I may have bare metal out there. I may have just a real-time embedded operating system like Nucleus running on some of those things. On some of those application cores, you know what? I can run a hypervisor out there. So now I can even have more separation out there. I can have Linux, Android, other RTOSes, bare metal, all on those systems, right? So now I got this complex system. How am I going to be able to communicate across all of these? So in the world, back when I started, it was like 68K and all that other stuff, kind of simple. And then there was like UPMs and PowerPC. It's like, oh, wow. Now we have all of this heterogeneous cores, multi-cores. How can I leverage all of that in a system that makes it beneficial to everybody out there? So you have a lot of different capabilities just within the hardware itself. So you have homogeneous multi-cores out there, where all the cores are identical. You have heterogeneous, that just covers like what I just talked about over there. Maybe there's 30 big little type setups out there. And then you have a hybrid that's maybe identical cores but are used in different ways out there. Maybe some high-end and low-end power options out there. Possibility for specialized cores, things along those lines. So how can you go about it from a software architecture standpoint? Well, obviously, if we have homogeneous cores out there, we can leverage SMP out there. And so we can take these application cores or these homogeneous cores and really leverage that capability in a SMP type environment out there. Provides higher compute for you out there, maximizes the possibilities of parallelism out there. Really, the OS handles a lot of this stuff with the scheduler and everything like that, and takes care of a lot of the complexities in the environment out there as well. And there's a number of RTOSes out there. Nucleus has an SMP version of it. Linux has things out there. So it does give you the capability of also having different RTOSes out there. Another avenue that we see people doing is asynchronous multiprocessing out there, or AMP out there. So leveraging maybe a specific set of cores out there for specific purposes out there. So this helps, maybe go from a multi-OS perspective out there. You can isolate certain functionalities out there. So if you have things that maybe need to be safety related, and you need an OS or something like that are safety on there, you can break those out into individual cores out there. It's well suited for consolidation of systems, right? So maybe you have different boards that were in the past, you're now moving them onto a single SoC. You can leverage some of those cores, those individual cores per setup, or a group of cores. Doesn't have to be individual cores. You can see in the example I have here, you can even have different SMP kernels leveraging, a dual core setup in a quad core SoC out there as well. But you still have the complexity of, okay, I got now this asynchronous multiprocessing out there, but now how do I communicate between those two? And more importantly, how do I even leverage the life cycle over here? So how do I boot these things up? Do I want to have a Linux? Do I want to have a Nucleus? Do I want to have a Zephyr? Do I want to have a FreeRTOS out there? How do I manage all those different systems out there, booting them up? How do I want it to be the master, maybe a remote out there? That capability. Once I get the system set up, how do I communicate across these heterogeneous type environments out there? Well, the OpenAMP framework provides that capability. It provides two functionalities. It's lifecycle management as well as the communication on there. So lifecycle management, they use remote proc, and then the interprocessor communication is RP message that's out there. So a lot of standards out there. If you're not familiar with OpenAMP, you can go just Google search OpenAMP. It's a Leonardo project now. It just switched over to Leonardo. Open source project out there. Mentor actually co-wrote OpenAMP with Xilinx back in like 2015-ish out there. And then Mentor actually has a multi-core framework. We call it the multi-core framework, but a commercial version of that OpenAMP out there that helps solve a lot of these really complex systems that are out there from that standpoint. All right, so what are some of the multi-core issues that we see, right? So you're going to run into, as I talked about, these inter-CPU communications out there. Inter-CPU safety capability. So imagine that system that we just showed where maybe I have a safety island out there that is certified for ASIL-D if you're in Autoland, right? But then I got some other cores on there that are more set up for application processors out there. Maybe so I want to run a safety certified version of an RTOS on that safety island, maybe something like a Nucleus safety cert. But then on the application side, it's more, it doesn't need to have that safety rated. It's not talking to any safety devices out there. It's maybe number crunching, or maybe it's connecting up to a cloud. It's doing other things out there. Or you can run something like a Linux on those application cores. So how do you keep the safe world safe and the non-safe world from contaminating the safe world? These are some of the things that you can look at. And with the multi-core framework and a cert version of that, it does help you with those type of dilemmas out there as well. Boot order. So, I have a system, I'll use the auto example, right? There's a lot of times when they have to have some type of traffic on the CAN bus within X amount of milliseconds of key on, they call it. So when you turn on your car, there has to be activity going on. And those are more than likely are talking to safety systems out there. But on the other side, maybe but that same system is maybe powering up a center stack or some type of cluster type things that's maybe running Linux on there. In that boot time, it takes a little bit more time to boot up the Linux over there. So as you're thinking about these things, boot order becomes important out there. In how you boot up the system. So be able to boot up something fast like a traditional real-time embedded operating system to get that important stuff going while the rest of the system's booting up can also be something that you have to think about during these things. System integrity is always one of those things that you always have to be conscious about as you start to think about these multi-core type systems that are out there. Management, right? So we have different flavors of management out there. We can have supervised that are out, or sorry, unsupervised out there, where you can leverage something like an OpenAMP, but you know there's still asynchronous out there. Or you can have what we call supervised systems, where they leverage something like a hypervisor, where you have this basically layer of software that's really managing a lot of the guest OSs that are standing or that are running on top of that, right? And then you also have, is like in that one of my first slides in it, a hybrid of that, right? Where you have some cores that maybe are running a hypervisor in a supervised environment, as well as asynchronous applications out there. All right, so here's an example of an unsupervised system. I have multiple application, I'm going to call them application or CPU processors, but then I also have some cores that are more traditional microcontrollers. Think of these maybe as a safety island or something along those lines, right? On top of that, I can now have all these different operating systems on here. So I have a possible, in this example, of 6 different operating systems. Obviously, they could be the same, just different instances of it going. And then on top of that, then we have applications that are running on top of those OSs. How do we communicate all between all those and get to that boot order? Well, that's something like the OpenAMP or Multicore framework can come into play to help with all of those quandaries that you may run into when you're developing a system like this, right? You can also have a setup like this where you actually have an SMP system on some of those cores with the traditional AMP. The Multicore framework or OpenAMP solution out there will work just fine with that as well. Taking it that next step further, same thing, right? 2 SMP systems be able to do that. Supervised out there, right? So we'll take a similar setup that we had before, and then have different RTOSs on here, right? And then obviously we have our applications that are running on top of that. But now we actually have a supervised system out there. So we have this extra layer, this hypervisor layer, that's managing all of the different resources and everything that's out there. So you may have to virtualize your networking or serial or other things like that, but the hypervisor is the one that manages or supervises those environments that are out there. And then obviously you can have a hybrid one over here as well, right? Where we may have a hypervisor running on some of those, but you still have the capability of having either bare metal or some type of RTOS running on individual other cores out there. And with the OpenAMP and Multicore framework can give you that capability of blending both the supervised and non-supervised worlds out there for you. Things to also think about over here, like mixed, some examples over here are mixed time domain, and where we're really seeing a lot of this is in the mixed criticality type environment. So here's an example of the mixed time domain out there where we may have hard, real deterministic capability. So where you run your traditional RTOS, right? So if I miss an event, do bad things happen? If the answer is yes, then you probably want something that's very deterministic. You know what's going on, things along those lines. Fast boot up, fast execution. Maybe you're in a resource-constrained environment for that because that memory area that you've assigned to those CPUs is small compared to the rest of the other ones. So maybe put in a Linux in there. You just haven't they didn't carve out or architect enough your memory over there. So you need something that can fit in that environment out there. You also, in that same system, maybe have other systems that don't have those hard requirements out there. So if you maybe miss an event or something like that, that's okay. You don't really, it doesn't cause any harm out there. Maybe you need to do number crunching or you have high-end graphics type capabilities out there. optimizing for CPU. So maybe you're running a bare metal type application. So here's some examples of having this mixed time domain to optimize your system based off of on this single SoC. In the past, this might have been 3 or more boards that did all this, and having that timing was it didn't seem as complex. Now they're all on a single SoC out there. Mixed criticality. So this is the one that we're really seeing probably the lead in these heterogeneous or multi-core applications out there. We see it in secure systems, be able to isolate different components of the system out there. We absolutely see it in auto and other type medical, industrial, anywhere where you have a functional safety type applications. Aerospace is another one. And certification. So if you need to start getting into certification, that can be expensive to go and certify code that you really don't need to certify. You can now leverage this architecture in the system to separate all that stuff that needs to be separated versus the stuff that doesn't need to be separated. And in some cases, when you're talking like $65 per line of code, it adds up. So being able to figure out, hey, what do I really need to certify and what don't I need to certify is huge out there. And be able to leverage the software, the hardware architecture to be able to enable those is critical out there, right? So certification, as I just gave you an example, it's expensive out there. It can also be time consuming. Size of code matters when you get into certified type environments. Less code, obviously less cost out there. And in the operating systems and everything like that. Typically the certification by itself, when you go and certify, you're actually certifying a lot of times the actual device itself. That includes hardware and software. And then on the software side, it's OS, it's applications, it's everything out there, right? So to be able to have something like a nuclear safety cert that has already done a lot of that certification, gives you all the test suites, and all the evidence for the specific certification you need, helps you get to market faster, helps you get through certification out there faster. And so getting into our example here, we can look at a system and expand on it and talk about mixed criticality. So now I got this certified RTOS out there, my certified area. So now I've broken up my application, there we go, my applications out there. Everything that needs to be certified. So I keep that small. It's typically, hardened, OS applications and everything like that. In a lot of cases, they call them safety islands, right? So dedicated processors that meet those requirements, right? If it's ISO 26262, 61508, whatnot, right? They have a SIL level on the hardware standpoint that meets that. Out there. And so be able to have that in there, and then you throw in the multi-core framework to help with that communication back and forth. And then with the multi-core framework and the certified version of that, there's also blockers in there to help prevent things that could contaminate from the unsafe world into the safe world from getting into that, right? And then you can also, on top of that, we leverage hardware capabilities out there. So I like to call these hardware firewalls that are out there, or zone of trust, so to speak. It's capabilities that a lot of the hardware vendors are putting in there, into their chips, to take that separation the next further. So not only is it a software separation, which is pretty good, but in the end it's software. It can be hacked or moved around and everything. If you're leveraging actually hardware out there, gives you now even more confidence that the safe world will stay safe and the non-safe world will say that there. So with all that, Mentor has that complete solution over there. We have the real-time embedded operating systems with Nucleus. We have safety versions of that. We do have Linux. We actually have 2 flavors of Linux. We have a Yocto-based and a Debian-based out there. We do have a hypervisor out there. To be honest, our hypervisor isn't certified because we actually put more investment and see more people leveraging our multi-core framework in the certs. We actually have a multi-core framework cert product out there. And then obviously, if there's connectivity and everything like that, we have an IoT framework with that. With all that, you need best-in-class tooling out there, development environments, analysis profiling tools. We get you all of that as well with our code sorcery code bench development environment. And then also we have a killer services team that can help augment for things that maybe you don't want to do or you're not experts in with that. And with that, I hit the buzzer right at, I see my little clock here is telling me 00, so I nailed it right on time. So if you have any questions, I'll be over there afterwards. If you don't see me there, if you actually want to see some of the capability with Nucleus as well as the IoT framework, we're in the microchip booth. We're on the back side, so feel free to come on by. I'll be here today and tomorrow over there, and thank you for your time.